Listo. Paso 46. Bueno, pues empezamos de una. Sí. Bueno, buenas tardes. Pues siendo las 2:36, vamos a empezar con este track que se me correspondió a mí presentar. Vamos pues hacerlo en inglés. Welcome to this track. The first talk today is Western state approximation of measures, the orthogonal frames, statistical and computational complexities. And the talk is by Daniel López Castaño. Daniel López Castaño is mathematician from the Universidad Nacional de Colombia in 2018, and he's Master in Science in Mathematics from the same university in 2003. Working on spectral geometry and non-commutative geometry under the supervision of Professor Silvia and Carolina Neira Jimenez. During that time, he completed a research internship in the Institute for Mathematics of the Universitat Potsdam in Germany, and he later engineered as BOSI, Latin American startup specializing in conventional AI. In 2024, he obtained a second Master of Science in Applied Mathematics and Statistics from Johns Hopkins University, where he is currently a PhD candidate in the same field, advised by Mateo Diaz and Soledad Villar. His research sees the intersection of optimal transport, Riemannian optimization, and manifold learning, with an emphasis on application of geometry to data science and machine learning. Beyond research, he devotes a significant part of his time to teaching and mentoring. Please join me in welcoming him.
Thank you, Alice, for the extended introduction. Yeah, so I am an alumni from this university. This is the first time that I'm giving a talk since I graduated, which was like before the pandemic. So it's been some time, and it's very nice to be here to present this to you, which is part of the research that I've done in my PhD, right? So thank you for welcoming. So yeah, this is some collaborators that I have with this for this work is Mateo, which is now at University of Chicago, Conway Yang, and Nicolas Garcia Tejos, both from University of Wisconsin-Madison. And yeah, so let's start with an example, give a little bit of context and motivation. So a very common problem in psychometry, right, is to understand personality types based on survey analysis, right? So imagine, for instance, that you have like different persons, right, different people. They basically fill up a survey, and now based on the answers, you want to say, okay, how can we classify these people? How do they relate? Which ones are, for instance, green? Which ones are oranges? Or which ones are red? For whatever those colors could be, right? Okay. So the mathematical statement of this problem is we're given a matrix. We have n data points. We have defined some factors, k of them, and basically we want to record the labels for each person associated to each factor, right? Okay, so this is something very well known in statistics. It's called factor analysis. Basically, the point is that when you have a huge, you have data sets and they often can be represented through few factors than the dimensions that you're considering. So some of these factors are correlated. So imagine that, for instance, you solve the questions for these 6 variables, and you want to basically, based on the answers of that, to say like, okay, yeah, we can associate a person with one of these factors based on the answers of this. So there are strong connections, probably with some questions, but probably some other weaker connections to those questions, right? So this is often described via a linear model, which here X represents the data, F represents the factors, and W represents the loading. So for each data point, how much of each factor are you representing? So interestingly enough, a lot of this data exhibits some radial structure. So imagine something like this. You have your data points. Of course, there are a bunch of them accumulated here in the origin, but you can perceive that there is like some radial extension, and basically you want to say, well, what is natural to consider here is like these 2 factors, which are orthogonal, and we would like to say, okay, so the person corresponds to this type of personality type if it is closest to one of these factors. Right? That's like the natural question. Also, if you see the data points there, you imagine like, yeah, I mean, probably putting a cross over there will be like satisfying based on what the data displays there. So yeah, intuitively, this means that the factorization will look like that. For each data point, you have the factors and the loadings, but the loadings associated with these factors are very small, and then probably you will have one that is very strong, and you say, okay, that's the one that will correspond to this person. So yeah, most of the information can be captured by just one factor, right? So the question now is, how do we recover the radial structure? So the natural idea, you have data points and you need some sort of directions that will describe most of your data. What people do with that is something called PCA, principal component analysis. That's very common. That's like the first thing that anyone would try in order to answer these questions. So this is what happened when we do PCA. Yeah, so you see, basically, it is not allineating with the directions that we would like to. Why is this? Well, the problem is that for this type of data, when you check the covariant matrix, right, this tend to be like a multiple of the identity, right? So when you want to find the principal components, basically you do the singular value decomposition of this population matrix, well, the empirical matrix when you have data sets. And then the point is, okay, so I'm going to pick the factors that are associated with the largest eigenvalues, right? But the point is here is that if the covariant matrix is just like a scalar multiple of the identity, but there are no really like significant larger eigenvalues. So basically it's going to pick random directions, which is what is happening here, right? So what you can find in the statistics literature is a solution called Varimax. So the idea is, okay, well, we want to rotate the principal components in order to be more interpretable in this sense. So the way that you find the matrix that is going to rotate and is going to provide you with these, I would say, probably more interpretable factors is via this optimization problem. And intuitively, this looks horrible, but what they were trying to do is to like capture the major orthogonal matrix that is going to maximize something like the 4th moment of the distribution. Why? Because empirically it has worked. There are not a lot of convergence or like actually like analysis of this type of optimization problem until like just a few years back in 2000 something. Yeah, the point is it was first formulated in 1958. If you would imagine, well, is this really like useful for something? So I would imagine yes, because there are a bunch of papers that cite this original paper. And also a lot of people uses Varimax rotations without citing them. Yeah, it's like these days you won't cite principal component analysis because it's too standard. So this is also very, very standard. I would say probably it's important as well. Okay, so what is going to happen with Varimax? for this type of problem. So, well, there are some, in theory, there are some convergence results from 2022. This is what they get. This is almost like, okay, well, the convergence of the factors that they can recover with respect to the true factors that define the data sets out of the order 1 over the 4th root of n and some logarithmic factor, right? But what is happening in practice, for instance, in this problem, is that actually Varimax is rotating the PCA components a little, but not too much, right? So what was the impression that we had with this? This seems to be like a very geometrical problem. And the thing is that they have tried to solve this via some purely statistical analysis. Yeah, and probably that's not the natural way to think about it. So it's not the most optimal, at least for this type of settings. So we have thought about that and say, okay, well, probably we should try to do something more natural. So what are the alternatives? There are things in the literature that you can find that could probably be used in this type of settings. So imagine, for instance, there is something called subspace clustering. The point on subspace clustering is like you imagine that your data points basically live in a union of some subspaces, and you want to learn the subspaces, right? So in this case, we could imagine that probably our subspaces are like orthogonal lines, right? We want to learn the lines, at the very least, as a union of lines, and there's some noise. So we will try to recover the best lines that we can. So there are a lot of applications for subspace clustering. And yeah, they do get better. They do get better factors, right? Is this the best way to do it? Not sure. First, because this method lacks robustness. So if you change the data points a little bit, so you sample a different batch of data points, the factors that you're going to recover are very different to these ones, right? The most robust solution, which is a very good paper, robust subspace clustering for 2014. In order to recover the factors, you will need to make some huge SVD decomposition of a matrix that it's basically of order n squared. So when you put that on a computer in higher dimensions, that's crazy. It's way too expensive, right? So, yeah, and for instance, in these specific settings, we try to look for orthogonality. And here, because we are trying to learn union of subspaces, it is going naturally to break the orthogonality. So yeah, the factors could correlate. So the question is like, okay, can we do something better, blah, blah, blah? Yes, we can. This is what I'm going to present. So if you see, this is our method, and that's very slightly more allineated factors over there. So yeah, this is the first thing that I try to do. Oh, we have some idea, let's plot it. Oh yeah, it worked. Okay, so now we work for 2 years trying to prove that this is good and consistent. And that is what I'm going to show. Okay, so this is the agenda. I just showed the motivation and some previous work. I'm going to talk a little, some short preliminaries in order to understand what we're doing. And then I'm going to explain the method, then the statistical guarantees that we have for this method, some computational guarantees that we have also for this method, and some numerical experiments. Okay. So the first preliminary that I want to talk, the first prerequisite that we need is to understand what is this Wasserstein distance. What is this? So this is an example. Imagine that you have, for instance, these 3 functions, right? And imagine that these functions are for, I don't know, like the densities that describe some probability measure, right? And you would like to say, okay, well, for me, this one looks just like this one, but just shifting some distance delta from here, right? And this one is a completely different function. So we'd like to say, okay, if I'm going to think about, okay, I'm going to start using a different language, but if I would like to think of a space in which I can think of points like probability measures, and I want to measure the distance between probability measures. So if those measures have densities, so they are absolutely continuous with respect to the Lebesgue measure, then we could say, okay, let's try the L2 distance between the 2 functions, right? That would be like the first thing that you would try. And what is happening there with the L2 distance is that these 3 densities are equidistant in terms of the L2 distance. So the L2 distance is not nice here. because it's not really telling you that you are literally transporting one measure towards the other one. It's just like trying to capture how much is the gap or of similarity between functions, and this is kind of like the average of them. So if this one is kind of the average of these two, but it's going to be naturally like equidistant. So what is optimal transfer? Optimal transfer is literally try to think what is the correct way for us to compare these probability distributions, right? So it makes it possible because we define a geometry of a space of probability measures, and we then get a notion of distance in this space, right? Okay, so how do we do this? So imagine that we have this setting here. So this is like one of the distributions that I want to compare with the other one. And the best way to do it is kind of thinking, how do we map each data point towards each mass towards the mass associated to other data point in other distribution? That's our problem. And it's very restrictive because you have to think about functions that are pushing mass towards the other side. But if you think about functions, you cannot consider, for instance, mass splitting, right? Because then that wouldn't be a function. So what is cool about this relaxation, this notion of couplings, is like, okay, you have these two distributions, you want to compare them, think about the joint probability distribution, right? Such that when you take the marginals, you recover the two other probability distributions, right? And what you're getting here is some sort of like a plan. To each data point, the mass associated, how this mass split in order to be mapped towards the data point associated to this distribution, right? So this is a better way. Of course, there is not a unique way to do that. There are a bunch of joint probability distributions that are going to map, that are going to have these marginals the same. So the question is, what's the best one? What's the cheapest one, right? And that is what is the definition of the Wasserstein distance, is between all the possible couplings, all the possible joint probability distributions. You are going to take the one that is going to minimize the effort of transporting the mass associated to some point x to some point y, right? And this is exactly the distance that we needed, because in fact, it is going to model what I was explaining before. The effort of pushing one distribution towards the other, that is completely captured by this distance, right? So that's the first thing that I wanted to discuss about some preliminaries. With that one, I can explain a little bit more about what is our solution, basically, of the problem with the factors. But the idea is the following. Okay, so you have your data points, right? You want the factors. It is clear that these two, this two frame is not the one that is optimal, because it's more natural to have this one. So what about somehow minimizing the distance between the points and the frames, if there is some distance that would do that? So in terms of the Wasserstein distance, we could say, okay, probably one thing that we could do is that think that the data is actually supported on a cross. And then you want to find the probability distribution that is going to be closest in terms of the Wasserstein distance. So imagine all the probability distributions that are supported on a cross with k factors, and we try to solve what is the minimum between the ones supported on that cross that is going to minimize the distance towards the measure mu, which is where my data is coming from, in terms of the Wasserstein distance. The problem with this is that it's an infinite dimensional problem, right? Because when you consider the space of probability distributions, that's too big, too big. So it's not a good way to parameterize this. But what if we can think better to parameters based on the orthogonal group? Okay, let's consider orthogonal matrices, right? And we want somehow to minimize around all the orthogonal matrices, the one that minimizes the Wasserstein distance of the measure and the projection onto the cross. Well, this is like the push forward of the measure with the operation of the projection, but basically what it's doing is taking the measure and projecting to the orthogonal frame that you define here. And between all the possible orthogonal frames, you take the one that minimizes this. So that's better, it's a better problem, because now we have something that is finite dimensional, right? So the dimension is of the order of d squared. So it's way better than what we were trying to do before. So in practice, what we are giving is some points, right? Sample for my distribution, and we aim to solve this problem, which is way more tractable, right? Okay, so this is what you see in practice. So we will call this, let's say, like this function, like the population version. With population, I mean that we know the distribution. And this one is like the empirical approximation, because we don't know the distribution, but we can get some samples from the distribution, right? And the idea to show consistency here would be to show that the minimizer of this empirical version of this one is actually approximating this one, which is the one that we want, right? Okay, so now the second part of the prerequisite is how do we optimize on a manifold, right? What algorithms are in order to do that? So let's imagine that we don't know anything about manifolds, right? We want to minimize the functions, so we have here plotted the sublevel sets of the function. And okay, so minus the gradient is going to point towards this local minimizer, right? And the natural algorithm that everyone considers to this is gradient descent, right? Now let's imagine that our manifold looks like this, has like this closed form, gx equals to 0, right? So there's a natural discrepancy here. On one side, the negative of the gradient is pointing towards this direction, but on the other side, the gradients of the restriction, if we try to solve this via Laplace multipliers, for instance, are going towards orthogonal directions. So it is not easy. You would think, oh, well, you know what? Probably we can just step towards this direction and then project back to the manifold, right? That would be probably easier. But the problem is that sometimes projecting is not that trivial. Because, for instance, if we consider the orthogonal group, that doesn't got like a good set. It's not like convex when you consider it in the embedding space. It's not that trivial to see that we have like, how to say, good properties in order to probably think, probably we can get like some property, probably about guarantees based on the description of the set, because the set might not be as nice to be described in terms of convexity. So yeah, this is probably not the most, the better way. But what about instead of considering this as a problem, optimization problem with constraints, we try to tackle it as an unrestricted, yeah, well, like you're optimizing over the whole space, but you need like some notions, intrinsic notions of the manifold in order to think like as a whole and not as something embedded in some bigger space, right? So how do we optimize without stepping out of the manifold? Okay, but this is what we would do in the Euclidean case. What we have here is this minus, which is telling us where are we walking, and this is giving us the direction in which we are walking. So there are two instructions here, walk and the direction. So in manifolds, the natural notion would be, okay, well, we need an intrinsic definition of a gradient. So something that is going to be telling me where should I be moving in order to not step out of the manifold, And we need something that would allow us to walk. So that's, in geometry, that's the exponential map, right? Okay, so we can think, okay, probably this is like the manifold equivalent of gradient descent. And the thing is that the exponential map is not something that is easy to compute always. Probably in the sphere is fine, but then if you want to think about more interesting manifolds, it's not that easy. So we can replace the exponential, but some weaker notion, something like a first order approximation of the exponential, which is called a retraction. So we have then the manifold, the tangent space of the manifold, which is going to give me the set of directions in which I could move. And then the retraction, which is going to be what it will allow me to walk closer to the point in which I am, because it's just a first order approximation, but will allow me to walk on the manifold, right? And there are cool packages that do this. So the one that I use is PyManoPT. The problems are very easy to formulate. The code is very easy to do, like 5, 6, or 7 lines will help you to just code the whole problem of optimization. So I truly recommend it. But yeah, now we have a way to think of this more unrestricted. In the mini course that I'm going to be teaching this week, so some part will be dedicated to optimization of manifolds, other part will be dedicated to optimal transport and the things about Wasserstein distances. You're very welcome to come. But now, okay, cool, excellent. Now we know that we have a way to, in practice, solve this. Now the question is do we have guarantees for this? So sorry about the long text. You don't have to read it if you don't want to. But I'm saying here is like there are some assumptions that are natural that we need in order to define this problem. And we basically have the population version of my problem. And then we have an empirical approximator of my empirical version of the problem, right? So now the question about consistency is like, okay, is really the empirical approximation approximating the true frame? The one that actually really models the measure when I know all the data and like I fully know the measure? The answer is yes, it does not just approximate, but it does in the best way that we can. So the best way that we can is because there is no something better than this that is called the parametric rate. Right? The best you can hope for is for this, and we actually reached that bound. So it was very good. Then you could say, well, yeah, you can reach the parametric rate with a standard M estimation. And I would say, yes, but this problem is not as nice in order to use the standard M estimation. I'm going to tell you why. Because M estimation is basically 3 steps. If you don't know if you don't know about this, I'm going to give you basically what is the steps. So the first steps is that you have control of the gradient error at the true minimizer, right? Then you assume that your gradient is Lipschitz, and by Lipschitz continuity and some strong convexity, you basically extend that in order to give local guarantees of the rate. But it's because of these 2 main things. One, the Lipschitz continuity of the gradient, and the second, the strong convexity of the objective function. So what is the problem that we have? The problem that we have is that we don't have Lipschitz continuity of the empirical objective, right? It's actually not Lipschitz, and we see why here. So this plot, imagine like this is the measure, the knowledge of the full measure. So when we think about the gradient, the Riemannian gradient, when we know the measure, that is what I call the population. So the 2 gradient in this 2-dimensional case look like the blue plot, right? Now we do some empirical estimation because we don't know the measure. We know samples of the measure, right? So for these samples, when you compute the gradient, you see that the gradient is discontinuous. In this 2-dimensional case, actually, when you approximate with a piecewise functions, they have to be increasing. But there are some decreasing parts. So definitely you will need to jump. There's no other way of being increasing and not jumping in order to approximate this. Why is this behavior happening? Well, easy. Imagine that this is your frame, right? The empirical version is that you can define like individual gradients and then you average them out, right? So the thing is like when you rotate at some point, what is ambiguous with respect to this frame, this cross, right? It's ambiguous in which sense? If I have a point over this cross, so I can project towards this one or this one because it's equidistant to both. So when you compute gradients, those ambiguity mess these things up. So how many ambiguities can I have? Well, take all the rotation, and for each point the ambiguity is touching one of these points, there you will have a jump. I will have a bunch of jumps if my ambiguity is actually 45 degrees away of where my data is concentrated. So I will have a bunch of jumps there, and those jumps are horrible. But when I consider the ambiguity set, when I'm closely aligning, okay, I don't have those many jumps, right? And the jumps are not that bad. So can we not just think about Lipschitz continuity, but something that is like almost Lipschitz up to some error in which we are approximating these jumps, but we can have somehow control of the jumps? That's like the question that we thought. And yes, so we do that. Now, why did I put this here? don't remember. Okay, but what is cool about achieving also parametric rate? Because it's not, the problem was not that the Lipschitz continuity. The problem was also that when you use the Wasserstein distance, it behaves statistically horribly. You suffer of the curse of dimensionality. That means you need exponential in the dimension numbers of samples in order to give a good approximation. But the problem is that if it's exponential in the dimension, then high dimensional data is going to be a problem because you need way too many samples, right? But no, what we see here is that we actually achieve parametric rate, which is the best that we can hope for. So why is the reason? Why can we actually, when we consider in higher dimensions, we are converging the same way that 1 over the square root of n, the parametric. And it's just not only for this data set, which is generated like by a mixture of Gaussians, but things that are heavy-tailed, like the double exponential or the student t, that also works, which is even weirder. But the answer is that we are assuming a lot of structure in our measure. You're saying, oh, these things look kind of an orthogonal frame, right? So yeah, we don't have course of dimensionality. Okay, so what's the idea of all this? So, okay, we're given a frame. The closest projection is this point over there, right? And now let's think a little bit about the geometry here. So, okay, I have more points. These are the closest one. So if I try to split the space into the closest axis, you will see that we are partitioning the whole space in Voronoi cells, right? These Voronoi cells are like pyramids, and towards each axis, you will have like 2 pyramids, like 2 cones, right? And the problems that we will have for the gradient will be for the hypersurface that is given where these Voronoi cells are, like where the boundary of these Voronoi cells are, right? So yeah, then based on this, what we will need somehow is to reason a little bit about how the measure behaves when I alter these frames a little bit. So if I alter them a little bit, like I rotate them a little bit, you will see that a lot of the mass is going to be within the intersection of the 2 Voronoi cells, and there's very small mass that is going to be these polyhedral cuts, right? That's kind of the reasoning that we have. Okay, so yes, I already explained this. I was going to show it because I was going to talk about ambiguity as these hypersurfaces, and you will see that the ambiguity is here in this 45 degrees away. But yeah, but I already explained that. Okay, so yes, we don't have the x, but because we have somehow the intuition that we can control a little bit the discrepancy between these Voronoi cells, we can reason about quasi-Lipschitz. What is this? That for most of points, we are Lipschitz, but for the points in which the Lipschitzness is broken, we can control the error of being Lipschitz. Yeah, that's kind of the intuition here. Okay, so now the question is, how do we control this resolution error? Why could we think that we control that? So this resolution error, if you decompose them, when you think, oh, by the way, I didn't define the notation, sorry about that. This is the empirical gradient. Gn is the empirical approximation of the gradient, right? U1 and U2 are basically 2 vectors that are some delta distance, and I'm going to do a uniform argument via epsilon nets, right? That's the point. So I want to have control within the radius of the epsilon net. And then basically I'm going to prove my property in the centers of the net, and then I'm going to extend it for the within the balls of each of these net points. It is enough. So when we consider this term, we can split that in 3 terms. One, well, because we are considering empirical gradients, we're basically averaging over n. Then we are counting here what is the max jump size that I can have when I'm close to my minimizer, when I'm in this like beautiful jumps that are not that big in this. Well, technically, I would call them the geodesically convex neighborhood around the minimizer, right? And there are some terms in the orthogonal group that will allow you like to quantify a little bit what is the radius of this geodesically convex neighborhood, but that's just for the technical part. But within this neighborhood that is well behaved, I would just call it like that, the neighborhood that is well behaved, the jump is not big. I have control over the jumps, right? So basically, the only thing that I would need is within delta distance, how many points can land, right? So in order to make this count, okay, so if we go back to the visualization, what I told you is that these polyhedral sections that are going to cut is what we actually need to measure. It's somehow like the symmetric difference between the Voronoi cells that we create here. The thing is that that region is horrible to parameterize and it's horrible to compute the integration. I really tried for months. It is really hard, right? So we needed to change the argument. I computed pages and pages of integrals that didn't make sense at all. They have horrible dependence on the dimension because, again, of the course of dimensionality. So this is what I'm going to show in the video is the intuition that is more geometric, and I would say is beautiful. So what we could say is that imagine that we could like normalize everything and project them in the sphere. So the closest axis operator is basically trying to compute the geodesic distance within the sphere, right, towards the center of the Voronoi cells. The bad points, the ambiguity points, are going to be points that are going to be closest to these boundaries, right? And the thing is like, okay, well, if we are going to reason about matrices whose difference in the Frobenius norm is at most delta, well, they will need to fall within tubular neighborhoods of radius of most 2 delta. And then if we can actually do concentration analysis to in each of these stripes, each of these tubular neighborhoods, each of these bands, well, how many of them there are? Well, there are as many as like d-2 geodesic hypersurfaces that are ambiguous. And when you project in hyperspheres, there are d times d-1 of these geodesic regions. So you only have to prove concentration in one of these stripes, and then you do union bound in over all the stripes. So it's just going to give you a polynomial term in terms of the dimension. So this is very nice, and this is basically what we got here. We have d times d-1, the stripes, and this is the concentration for each of the stripes. This quotient here is like the quotient between the surface area of SD-1 and SD, so the unit spheres, and asymptotically, I think this Bale's inequality or something like that, that this goes like the square root of D. So this is like D2 d5 over 2, more or less. Also, you can bound that with the gamma function properties, and that also works. So this is fantastic, because if I have a square root of n here, I just replace it here, and when I divide it by n, I get 1 over the square root of n, which is the parametric rate. That is the idea of the consistency here. And then, probably I'm not going to explain this. Each of these things is a proposition, but if we go step by step quite far, the first one is true because of geodesic strong convexity of the population version of the objective function. The second one is a uniformity argument. So there, basically, you use, because these things are sets, the empirical gradients are not really gradients, but subgradients, so they're sets. So when you do triangle inequality there, you have to be careful. But once you reason a little bit, you can get to this sub over there. And then we do the epsilon net argument. That is, we prove all the things point-wise in each of the centers of the net. And point-wise, we can use a standard CLT here for M estimation. And then we somehow want to control this uniformly over cells of radius of modes like delta. And this is the rest of the argument that I just provide, which is okay. Let's do the point-wise CLT and the quasi-Lipschitz nets. Then we observe some constants, and then we get to the results. That was a statistical guarantees. Now, how do we get to the empirical minimizer? We don't have an exact way to do that. We have algorithms that computationally are going to try to take us to the empirical minimizer. So the algorithm here, of course, natural, is Riemannian stochastic gradient descent. And I'm not going to focus too much here, but basically what I'm saying is that what we can get through the algorithm, after the iteration, that matrix in distance gets the same rate, because you take the square roots here, right? Gets the same rate in expectation. Expectation is a bit weaker, that way we have in high probability before. But if you add some conditions, for instance, that you have a distribution whose states are sub-exponential, then you can transform this in a high probability result, which is the same that we have for convergence, right? So this is really cool because in one side, we prove statistical guarantees, right? We do not suffer from the Coulson dimensionality. In the other ones, we provide computational guarantees, and we actually have here this linear convergence of the algorithm. That is really good. Now let's compare to the other methods. Okay, this is what happened with the other methods. Remember Varimax, the first one that I talked about? Well, the error is horrible. It's like 2 scales away with the errors that we have. Subspace clustering, the one that is learning the union of subspaces, that one that's better in smaller dimensions. But in higher dimensions, we do better, right? Okay, that is in terms of the dimension. But in terms of the noise level, okay, also these two are better, but then at some point where you have a lot of noise, the subspace clustering is going to do bad, we're going to do good, okay? Nice. Now, in terms of computation, so basically, in computation, the bad methods, they're not bad methods, but I'm going to call them like that. The bad methods are really fast, right? Subspace clustering, which is like the intermediate one, is really slow. And we are almost as fast as the bad method. Okay, so there is no even like computational difference there. And also in terms of noise, we also do fast. Okay, cool. So compared to other methods, we are good. Now let's talk about application. Why do people care this? So the first thing that I discussed about psychometry. Okay, yeah. So basically, what we did will allow us to make this clustering, and then we can identify types of personality based on which cluster are you closest. I think that's the most natural one. Now, for instance, I have here like the New York Times articles. So this like a huge matrix in which each of the rows is like an article. And for each of the columns, you have like all the words that are in English, right? And then you put a 1 if the word is present in the article. And then what people do usually is to run PCA to see what kind of factors can we recover from this. So when you do PCA, you see that this is kind of the factors that you have. And centered towards the principal components. So you see like these radial spikes, right? And when you run our algorithm, actually the radial spikes show that you can find the basis in which the data looks sparse, right? So you have a bunch of zeros and then like a 1 or something that is not close to 0. Okay, cool. I love this application, right? This one is related to climate science. So a lot of climate researchers study some spatial variables. So the variables is like, imagine that for each pixel value, you have like time series data. So at different points of the time, your pixel is changing the values, right? And then you have a bunch of time series based on each of the pixels there. But when you want to study anomalies, this is huge dimensional. So, okay, what people do is find the anomaly covariance matrix, which is trying to do kind of the same that I explained before with PCA, because they do PCA, right? Well, we ran our method and we found this. Does anybody know how this looked like? No, this is El Niño. Okay. So this is El Niño phenomenon. And because this can be biased, if you take the whole world, well, you could zoom in to see how the other components look like. And when you look at them, the first component will be associated to the Niño, but actually the second component, the most important one, you will find when the temperatures go down, then you will find La Niña. Okay? So this one is really cool. And this is another one that is very famous. So you have the faces data set. You want to try to find hidden factors within the faces of a bunch of people. And this is what PCA gives you. This is in 2 scales. This is grayscale. This is some weird CMAP. And then when you do Varimax rotation, which is supposed to give you like a better interpretation of the faces, they actually corrupt the faces. The faces are not nice there. When you run ours, you actually see that we have some things that are quite different for the ones that you get from PCA, and are almost like kind of interpretable as well. If you were interested in these things, I don't know. But this is a very famous data set, so I wanted to run it with you. Okay. So, in summary, we constructed a method that uncovers latent fewer factors, the linear combination of correlated variables. This method is scalable, achieves better statistical performance than other classical methods. We provide optimization guarantees for this method, and we demonstrate its applicability in real-world data sets. And that is it. Thank you.
Daniel, thank you so much for your talk. We have time for 1, 2, or 3 questions.
Thank you, Daniel. That's a wonderful work. And I was curious about this linear nature that you have there. It's because the scale of the psychometric instrument. I mean, we use when we devise this psychometric instrument, we use Likert scale, but it is related with that, or what is the reason? Because you have this pattern, this like X pattern there.
What you're saying is like, why do we see data that has like the radial structure?
Yes.
Yeah. I mean, this is a very specific setting, right? We've seen that there are some cases in which you see that because there is like this weird radial structure. I think it's because it's data that by itself seems to be describable. It can be described by a single factor. So it's for those cases that we do this. When we run it actually with things that are not exactly like that look like crosses, but are like let's imagine like one factor that is like the main factor, and then something that is a little bit correlated, so it's not exactly orthogonal. In those cases, well, we are just fitting the best cross, right? Which is like as explainable as possible of the whole data. And when I say explainable as possible, is because these orthogonal directions are like giving you like more description of what is within the whole space when you look at the projections towards it. There are some cool applications that I've seen in computer vision, because I'm not an expert on that, and those papers, I read them like 2 years ago. I didn't remember very well how they were about. But I remember the thing that I remember is that they did care a lot about the orthogonal directions, because it seems that because they wanted like one-dimensional projections in order to get as much of description of the space as you wanted, they were thinking about this type of body max rotations to get like this absorption of information in factors. I think that's the explanation that I can give, but yeah, probably there's a better.
I have a question. So your method is like a dimension reduction, right?
Not exactly, but it's like the second step after the dimensionality reduction. So imagine like you do the dimensionality reduction via PCA,
Yes.
and then you want your like the basis of the subspace that you find, you want them to be more interpretable a little bit.
Okay.
Or you want, like, for instance, the basis to be like as sparse as possible.
But my question
Yes.
is not that. But you say that this works better when the points are in a radial shape, in a star shape.
Yes.
And how do you measure that in a point? If I have a set of points, how can you measure that the points are in a radial set?
It's not trivial. It's not trivial at all. That's a good question. Yeah, why the faces have? Do the faces have this radial structure? We don't know.
Okay.
But the best we can hope for is to run the algorithm and to see if we get something that is meaningful, at least.
Thanks.
Yeah, I think that's.
Room for another question?
Yes.
When the people use these varimax and all these things, they have this high level of interpretability. The factors and the values and all these things. The results that you have there are also interpretable, because most of these methods are used by people in psychology or people that is doing that psychometry.
Yes, no, I truly believe they are. We are like providing the mathematical method that we believe are going to be useful for them. And we try to like find many data sets in which we can show that this is useful for whoever person is interested in those things. I think, yes, that's the hope. Even though we are not trying to prove that we have like the most interpretable method. We believe that this method is easier to interpret, like when you have like these bases that are at like random directions, for instance, when you're on PCA. So yeah, I think that's what I could answer for that. Yeah.
Okay, I have two questions. One is how do you generate this graphic of a square frame error? Because the one axis dimensions and the other.
You mean like the video?
Exactly.
Okay.
No, the graphic, like the graphic when you show the results. There is. How do you know that one? That one. How do you generate that? Is experimental? Do you generate?
Thank you. Yes. That's nice. Good question. So yeah, imagine that for instance, here, what you have is like a Gaussian mixture. So imagine that you have like a mixture of Gaussians whose covariate matrix is something close to having a lot of probability of being in one direction and like a smaller probability of being in the other directions. And you do that for each of the axes. So you have like a cross, but like the tails are Gaussian. Here we do the same, but the tails are exponential. And here we do the same, but the tails are student t. In theory, what we provided was consistency for this type of data. But what we are showing here is that the method is robust because you can like use distributions that are outside of our assumptions for our proofs, and still it works. So here we have, for instance, the linear convergence there. And also the other plot, the one that shows the statistical, this one, it is the same. When we run it with the student t and double exponential, we still see the parametric rate, even though those things doesn't satisfy the assumptions that were natural in order to solve this problem. So another question would be, how can we like soft the assumptions a little bit more in order to include a broader class of distributions?
Yes, thank you.
Thank you. What's the other one?
Yes, and the other question is maybe to motivate our people here at the department to your mini course. I don't know if you can tell us maybe in 1 or 2 minutes.
What is the course is going to be about?
Exactly, and maybe why interesting for a mathematician or a statistician or people of computer science.
Oh, I see. Okay. Well, the course is about a lot of things that I consider fun to study, but I would say, okay, so I was very skeptical about applied math when I was doing like my undergrad and my master, because I didn't like take a class in statistics. But when I saw like the statistics books, they showed a lot of things that I didn't like, and I was like, no, I like more geometry and topology, and the analysis. So I was like more curious about learning those things, but also because every time that I had to took like an applied math course, I didn't like it, right? So it was like, but then when in the PhD, I found like very interesting to see that there are good geometric ideas, good ideas about related to functional analysis, good ideas about related to topology, that you would see that the ideas are mathematically very interesting, but also the applications are something that at least you can see them on a computer, right? Which is something that when we study, I don't know, compact operators. What is a compact operator for you? The only thing that I could imagine that is like a matrix if I think about things finite dimensional, right? Okay, so it's a little bit about that. Like there are good math in things that are very useful, and that's nice. So you're invited. The content, as I explained, optimization of manifolds, one session, optimal transport, another session, and then a third session if we have like enough time. I will show you, for instance, that when you consider the manifold of probability measures with finite second moment, and you take the Wasserstein distance, which is going to be like the natural Riemannian distance that you consider in this space, and you think about dynamics, like Wasserstein gradients or things like that, they are very related to very famous physics equations, Langevin dynamics, Fokker-Planck equation, porous media. So there are two ways to see this. It's like, okay, the Lagrangian and the Eulerian way, but basically what you're going to describe is that when you have some set of particles, you through this Wasserstein distance, you see how do they evolve in space. And like what's the probability of this thing moving after some weird Brownian motion with Fokker-Planck dynamics, blah, 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 going to the other way. So this is like a probabilistic way to study that. So I like it too. I am not a physics person. I really don't understand a lot of things about physics, but it is very nice to study this type of geometry.
Let me just add that it's tomorrow, Thursday and Friday, in
yes.
the mathematics department.
Okay, thank you. Yeah.
Yeah, the course will take place at the mathematics department at the room 2000, so that you are invited. Okay, thank you, Daniel. Thank you. For a half hour, we return at 4 o'clock. So you are welcome to our next talk that also bridge these two fields of computer science and mathematics. So you are welcome to
Optimiza la variedad para que
Así es.
lleguen los datos.
Así es.
Pero me perdí en que te dije, bueno, a mí me saben que en algún momento.
Sí.
Y me perdí en qué punto.
Entonces lo que pasa no está bien. Lo que pasa es que nosotros probamos y cuando usted coge la distancia de base, trata de buscar cuál es la medida soportada en una cruz, en una crisis, frame, bueno, que es más cercana a su medida real. ¿Sí? Hay un optimal transport. Hay transporte óptimo map que va a ser realmente solo la proyección. Entonces ese doble problema de optimización porque hay dos. Uno, el mínimo con respecto a todos los frames y el otro, el mínimo pero con respecto a todos los transport plans. Claro, es doble. Entonces este mínimo se resuelve porque se vuelve el objetivo poblacional. Es una forma cerrada para la distancia base.
Está esperando que va a
Sí, claro.
Sí, no.
Sí. No, esa es la razón. O sea, hay un transform map. Entonces es muy chévere porque se puede decir, sí, esta es la transformación, la distancia base va a ser simplemente como tomar el expectation, el valor esperado, perdón, esperado con respecto a esta variable aleatoria que es como X menos la proyección.
Creo que
de hecho, acabamos de terminar y es una escala como se hace una cosa real.
Sí, claro.
Usamos métodos estándares.
Oye, esto es súper bueno porque esta optimización en variedades es solo ese paquete y de verdad ya todas las funciones están muy optimizadas dependiendo de la variedad que es de su interés. Las variedades que estamos funcionando acá pues son como matrix manifolds, como matrices unidas o enteras o esto, matrices ortogonales. Entonces, para eso, digamos, el paquete es muy bueno porque es lo único que hace es como llamar a sus métodos y define su función objetivo, lo reminimizar y esa vaina le calcula los step sizes, todo lo que se necesita. Mierda, eso es cuento con la reacción. O sea, el paper está listo hace 3 meses, pero el hombre tiene una manera muy específica que le gusta que las cosas estén escritas. Hasta que lo sienta y reescribe un montón de vainas al gusto de él, no sabe nada. Entonces estoy esperando. Porque obviamente él tiene muchas cosas, entonces se va a demorar toda la vida. Pero
los datos
me parece yo tengo un estudiante de máster que está trabajando conmigo, que está corriendo métodos de estas cosas. Y a eso no es más acá también pueden estudiar fácil. Pero sí, mándame los datos, un chequeo. ¿Lo tienen en un repositorio igual?
Sí, también es importante que vean que la parte
De una, yo chequeo. De una.
no se preocupe que no
Ok.
de buenas a pedir.
Sí, con gusto. Y a mí me alegra. Me alegra. No, está. Yo tampoco, yo ya no me acuerdo de lógica.
La vida me Política y son profesores de la Tecnológica de Monterrey. Entonces, están en computación. Y con ellos hemos seminario de categoría. Entonces, no tengo parado, pero obviamente estoy pensando como
En esas cositas. Sí,
aprendiendo.
Sí, no, es que sí, la movida está muy para allá, ¿no? Incluso, o sea, realmente de aquí a los libros como que el matemático que trate de trabajar va a estar. Y es un debate ético y complejo también. Sí, porque, bueno, en fin, o sea, igual la inteligencia artificial resuelve un montón de problemas muy importantes. Entonces hay que empezar a aprender a usarla y usarla.
Y el asunto son que categorías para eso a las monografías.
Ok.
Claro, estamos muy cerca de los RN.
Claro.
Entonces, ahí está el bueno.
Sí, yo igual no entiendo casi de eso, pero sí, hay muchas cosas. A mí me sorprende esto cómo se conecta con tantas cosas de la matemática. Porque, o sea, yo era súper escéptico, ¿no? ¿Cómo es? Yo era súper escéptico por ejemplo, pues, para mí estas cosas era como eso, piquear una curva. Así que va, piquear una curva está resolviendo problemas abiertos en matemáticas. Entonces, no es solo eso.
No,
Hay unas cosas ahí bacanas.
entonces, pues igual aquí. También me pregunté por ahí lo último que dijo Francisco, queriendo ver el campeonato.
Ah, no, yo sé. Escucha.
Con calma, sí.
Sí, me toca.
Con calmita, porque
No, pues que ya está. Y de hecho le podemos hacer preferencia como 80
porque
este hombre hasta que no lo lea todo.
Porque
no
el
sabe.
asunto es que
Sí, Juan Felipe, claro.
sí, claro, yo estoy intentando mirando cosas con él y con Gio.
Ah, ya. Sí, ya.
Entonces realmente
Sí,
mi conexión va a ser por ese lado con él.
Carmona, sí, claro que sí. No, yo también, yo lo tengo en LinkedIn y él está metiendo el duro al día.
Sí, entonces el asunto es que estoy representando con y la idea es como...
Igual a mi computador.
Uy,
No, mismo me asusté. No, yo no tengo que hacer nada, pero...
Oiga, yo sí,
De una, o sea, apenas está acá, le mando un correo con el PDF y lo escribo.
Listo, vale.
Bueno, Pedro,
Vale.
muchas gracias por...
Listo, no, chévere, bacán. No sé ni un carajo, pero bueno, la idea es saber si
Sí, yo también ahí aprendí, yo tampoco sabía nada.
No, sí, no, y el asunto es que
Sí.
ya poquito.
Así, sí fue como Diego también un poquito. No estaba tan metido con el cine y eso. Ya me entiendo. Y pues me llevo la vida.
Hablamos ahorita.
Sí, tiene todo sentido, porque eso es como intuitivamente es lo que un average design process es, o sea, es como ya en vez de proyectar un tren y como proyectemos en una dirección y como miramos los averages, o sea, que es una medida de
O sea,
este es más
no, son que tienen más tiempo. La convergencia de las
eso que ver, sí,
pero
es como también la optimización pero que quizá es más y ese resulta muy bueno para poder otra medida nueva cuando alguien quiere conocer sobre la medida completa, ¿sí? ¿Cuál es el mejor? Ahí puede mejor de la sensibilidad y está viendo de la eso lo comparte y funciona muy bien porque porque esas proteínas tienen como estas formas elongadas y lo que se está encontrando precisamente cuál es el eje que le describe la proteína, ¿sí? Y cuál es como la simetría.
Como análisis de
Eso podría más o menos
como que
es más bacano.
mucho más pero no espero que por la distancia me parece
No.
porque exacto, lo que quiere explicar buena la charla. Para los estudiantes de maestría de matemáticas, pero solo uno, o sea, solo hasta menciones y el máster.
Yo tenía miedo porque como eran varios slides, yo estaba cansado.
Ah, sí, es que no lo cogí.
Como pues, dale.
No sé, a media hora pero
una cosa.
Primero porque si es la como un embudo acá en el nacional, entonces no hay una sobrepoblación de estudiantes de matemáticas. Por la ciencia de la computación también es obligatorio de las universidades. Entonces ya hay dos, o sea, tendría que abrir otro grupo especial. Y no creo que ahora, porque es que interesante, ¿no? Porque se va a intentar desplazar. Porque la sí, entonces, y segundo, los estudiantes de estadística, o sea, ¿saben que eso?
Algo bonito con 10. A nada con 10. Voy con algo bonito y no
Entonces la gente, o sea, digamos, sí, exacto, es lo que pasa. Les tocó abrir un solo grupo para estar monstruoso. Bueno, era otro pedido, pero o sea, que un grupo adicional de
no, algo de recuerden que son los tres sistemas que están en la cara y lo analizar es lo de por eso es la presentación.
No, claro, un chico que también Esta sesión la grado la más de nuestra moneta exposición diferencial. Porque pues en eso no puede, o sea, como es un cálculo, uno medianamente no puede tirar un libro.
La prueba de
Creo que es mejor que tener un micrófono que lo que ahora. Claro que tenga accesibilidad. No, y la mayoría de gente está diciendo que lo que es mejor más. Lo que yo lo he nombrado, pero estamos en más que no, tan riguroso.
No, pero yo no he nombrado, pero ah, no, yo te escuchar. Ah, esa es la distancia con es que eso es fácil porque tiene ya se tiene cuando yo no en la calle o no en la casa no toca ver, pero veo usted lo único es que está doblado, ¿no? Que no habla hay alguien que no está, hay alguien que ya no habla encima. Yo, la verdad, eso no es súper fácil, eso lo pueden hacer. Lo primero que está usando uno de maná, es una de las más y la Emma, ella te decía, es una la carrera en investigación. Como ese sí, el mantener es insoportable. Es bueno, leerlo es interesante, pero tiene incluso para francés.
Bueno, ahora agregado.
Claro.
No, no puede ir porque está tan acelerado.
O sea, la usaba como conceptualmente, está haciendo eso de para invitar, o sea, estaba analizando, entonces después hablamos y colgamos una invitación. Cuando ya después no,
Por eso es por eso muchísimos trabajos en
Pero, profe, o sea,
ah,
bueno, pero no puede ser.
bueno, es que tengamos el
bueno,
ok, cuando yo trabajaba
profe, yo le escribí que sí, o sea, como la anterior semana sí se podía, pero como esta vez no podía. Mañana en la mañana, pues.
Sí, esto no es fácil. O sea, para el curso que se le eso es para finanzas, pero creo que va a haber digamos, por la tarde.
O tiene las conferencias de acá, porque pues hay conferencias.
Ah, usted vio cómo ganó. Yo vi cómo un alcancé a ver como 2 semanas. Cambio mi inglés, algunos si no puede lleno de esa optimización, pero lo poquito que vi en esos lugares era muy avanzado. Sí, esos gigantes eran muy avanzados. Muy bueno. Entonces, la idea era la discusión. Pero la media que era más óptica de acuerdo. ¿Cómo te describo? Sí, creo como que va a ser. No, se ve la media, el numérico 1. El de marco y como que 3 veces me dan al transporte. Ah, ya, no, modelo lineal de generalización.
Y aplicar el
¿Pero profesor Vanegas?
no le toca sustentar.
Es un modelo lineal. Sí, ya de ahí las cosas fundamentales. Es que utiliza amigo tuyo, pero sé que estoy esperando. ¿Por qué, profe? Sí, ¿no te crees que sacar un buen tiempo? No, entiendo. Sí, yo creo que... De hecho, colocar como recomiendo, o sea, bueno, sí, es lo que yo quiero, o sea, es lo que me encanta del departamento de matemáticas, que todos los semestres están también conmigo. Yo soy profesor asistente, y la profe del grado no, no, es sí, o sea, no, eso me comporto que no tengo que preparar. Sí, eso sale. O sea, es muy duro para ver en dónde puedo explicar o qué pide. Sí, prepararlos. Y lo damos, porque uno pensaba lo que piensas. Uno queda con la idea de cierto nivel. Pero ya después, digamos, pero luego sí, ya es más sencillo. Entonces, eso me parece chévere de importancia. Sí, yo creo que María, como está en el purgatorio. Pero, digamos, lo que nos mandaron en el formulario sobre el modelo, como, no, dije, bueno, modelo y otras recomendaciones. Sí, fue. O sea, como ya voy a los horarios. Yo no me puedo no, no sé, es que yo cada vez
Pues no exactamente.
Justamente cuando el tema de los se hace la próxima. No. Ay, sí, yo amo ese curso, porque yo vi en pregrado que les está
Pero que para nuestro servicio.
Así es pasar ahí, o sea, no, que porque, o sea, bueno,
Y cuando hizo el modelo de
yo lo que lo es que yo digo la estadística
debería mandarlo.
convocarlos,
O sea, la lista que se tiene es tener 5 semestres cursados. Si tienes, ¿cuántos grados? 7.
Pero, o sea, no.
Sí, porque
Pues igual no lo pedí y ya fue. Por el certificado dentro de la universidad. Un periodo clínico, pero me dijeron que ya puedo empezar a hacer.
Ah, sí, pero cuando lo pedí,
Creo que él va a hacer algo de pero probablemente si no puede avanzar más, es que desde la comisión es el mínimo de las elementos para cada uno. Tiene que ver los situaciones generales
Fue una regla. Solo fue.
¿Qué pasó? ¿No sé? Pero yo sí no quiero certificar, es una diferencia. Lo continuamos, podemos aprender cuando
yo no sabía ni siquiera que estaba ahí. Tengo una pregunta. Ya me
Vamos un minutito, arrancamos.
Bueno, muchas gracias por continuar acá. Thank you so much for being here. We finished today, I think, before the reception, with this second talk on this track, after the track, entitled Logic Meets LLMs, Attention Has a Logic, by Miguel Moreno. Miguel Moreno is mathematician from here, from Universidad Nacional de Colombia in 2010, with a thesis on representable matroids advised by Professor Humberto Sarria. He completed his master's degree at the University of Bonn in Germany in 2013, with a thesis on the stationary tower forcing under the supervision of Peter Koepfer, and his doctorate in the University of Helsinki in Finland in 2017, with a dissertation entitled Finding the Main Gap in the Borel Reducibility Hierarchy, advised by Tapani Tignen. Sorry if I read the name. He subsequently held a research position at the University of Maryland, Israel, and the University of Vienna through a Lies Minor Fellowship from the Austrian Science Fund and the postdoc pool from Finland. And he is currently a postdoctoral researcher at the Mathematics Research Center at the University of Tampere, working with anti-system. His research combined mathematical logic, automata theory, descriptive complexity, and machine learning to study the expressive power of modern neural architectures. His most recent work concerns logical characterization of transformer models with connections to temporal logic and distributed automata. His earlier work was in model theory and generalized descriptive set theory, with publication in journals such as the Journal of Symbolic Logic, Fundamental Mathematician, the Israel Journal of Mathematics, and the Annals of Pure and Applied Logic. Please join me in welcoming him, please.
Okay, well, thank you very much for the invitation. I'm very happy to be here and presenting this work at the National University. I'm very happy. I hope you will enjoy it as much as I will hopefully enjoy it giving the talk. Yeah, so as Arlie said, I'm coming from set theory and model theory, so this is quite recent research where it was finished in May of this year, so it's basically out of the oven. So I'm trying to give it like a very intuitive representation, not so to go too much into detail, so you have like the intuition what's going on. So let's start with this. So I will address some problems in LLMs. It is basically, it's a black box. So let's start with the motivation. So we all know that modern computational, we are using basically all the time neural networks and AI. It has been shown that it's very powerful, even that recently every week we get this news that an AI solved an open problem or something in mathematics. So it is quite powerful so far. And the thing that, so neural networks have existed for a long time, but the recent boom happened with the transformer architecture. That is from the paper, Attention is All You Need. That was the one that led to ChatGPT and all these large language models and chats that everyone, we all know for now. But there is a problem, and is that these models are basically, we're using them in a heuristic way. We know they work, but we don't know precisely why. Quite a very big black box. We kind of have an intuition what's going on. People develop these with some kind of intuition, but it turned out that it was working, and we're trying to understand what it is. Like, it works, and we understand it in a heuristic level, but the question what's going on, it's quite not so clear so far. So what we do in this work is that we attack this problem and this weakness. We try to give some kind of theoretical background of this problem, and we use logic to understand what's going on and what's pressing power. So, continue to the big picture. So, the big goal is to answer the question of what's going on. But everything, it is coming from a simple question, and it's like, what kind of transformer architecture compute? What can they do? What can they say? What can they compute? Because we know that not everything is computable, so obviously there will be some limitations. So this is the main question. It's a simple question, but it's a very big, interesting question. So we, in our work, oh, I forgot to mention, this is joint work. It was in the first slide. It's a joint work with Betty Appian, Andy Kuzisto, Damian, it's from the whole logic group in Tampere. I just forgot that it was to mention it about joint work. Sorry for that. Okay, so we start just by the encoder-decoder architecture. So it was the first one, the one that it was presented in the Attention All You Need paper from the researchers from Google. So we focus on that architecture, that initial transformer architecture. Nowadays there are some others that are a bit more complex and so on. It has evolved, but we're going to show, we work with that one, so we're going to show the results for that one. It has evolved now because it's a very rapidly growing field. So we use temporal logic to explain, to give an idea what's going on and express power of transformers. And we also use distributed automata, that is kind of the same as a neural network. You will see that it's quite natural to understand this. This slide, we prepared the slide, the whole group, so that it is natural to understand. There are no technicals. That's the picture I draw some minutes ago. The classic or the sequential typical computing. Okay, so and now this is what it's called distributed complexity, the software computing. So the input is a graph. Then we place the algorithm in each node. Now we have the distributed system. And then the local passing. So each arrow means that, so is that this one is sending one to here, this series going, this one is sending this to here, because the arrow represents a query, basically. So it's, the arrow is, this vertex is asking for information to this vertex. This one is asking from here, this one is asking from here, this one, okay, this one asks from here and here. So it's a bit counterintuitive, but it's basically representing the query. Like, what is the vertex interested on? So you can see we just zoom in a small part, then this vertex is asking for the message to this one and to this one, and they are sending the message back. So that is a distributed computing. So let's work with an example. So let's say the reachability problem. So we want to say who is reachable by who are reachable. So the source is the green one. So this is the first iteration. This is how it starts. So the one on the left is reachable, and then it sends the message to the next one, to the second one that it is reachable. So now the second one that know that it is also reachable. So it sends him, the message propagates to the nodes by neighbors. And then the next one is that it is reachable. And finally, everything was reachable in this graph. So the root gets the message, and the root was the one that was asking the query, asking. So yes, asking. Okay, so now let's give a more formal definition.
Sorry, but you said it was the same algorithm in each circle.
Yeah.
And but the first one somehow knows already that it's green. It doesn't seem to be the same as the second one, which is already green.
Oh, yeah, because it's reachable is that this vertex is reachable. That's the question.
No, but you have to have the same algorithm in each circle, or can you have different ones?
No, you have to have the same algorithm.
Yes.
And here the algorithm is basically the identity, like it's asking here and it's just putting the one.
Yeah, the leftmost one seems to be doing something different. It's not waiting.
Ah, you mean because of the first?
Yeah.
Because of the first one? Yeah, but because it's the initial state. So the initial, you start with something and then you will start applying the algorithm. That's the thing. So a distributive system is we have W, R, and some parameters. And then we have the automaton, that is the algorithm. So in each node of W, we put a copy of the automaton, that is what I'll be calling an algorithm. So we put a copy of the automaton. Then R is just the communication channel, so basically the arrows. And the PIs are just subsets of W, are the predicates and the possible. The codes like the possibilities and so on, the possibilities for the states, but it's labeling each input in each node. So in the I input bit of the node W, we put 1 if W belongs to PI. So that's a distributed system. So it's just you have like kind of a matrix, and you're saying that the I input is in this characterization, in these subsets, and so on. Good. Good. So now let's talk about the automaton that we were putting in each vertex. So we will talk about finely distributed automatons. So FEA. So we have that is Q, delta, pi, and F, where Q is just a finite non-empty set of states. So it's where we were going to have, like, for example, this piece on stuff. So delta is the change of the transition function, so how the state changes. Yeah, it depends on, it goes from Q on the power set of Q into Q. This is how it's changing the states. This depends, as we said, it depends on the nodes, like in their current state, and the nodes of the neighbors. Because we know that it's affecting it's in some kind of a neighborhood of the vertex, or what's happening there that is affecting the state of the vertex. And pi is some initialization function for the labels, for the labels of the pi. No, pi is, or is it pi? Oh, is, let me just give me one moment. This function from no. It's just the point. Oh, yeah. No, pi is just some. What it was like. The initial, the W, the labels you're putting, it's just a set of labels. So you're putting labels like W1 or something, it's just some labels. Yeah. Pi is a set of labels, and sorry, no, it's not an empty set of states. Oh, no. Why? Function from node. Yeah. The nodes labels, yeah. Because you have the vertex, and each vertex has a node, so the nodes labels just go to an initial state. So we will see later what is this pi. This power set. This is going to be the tokens. We'll talk about the transformers. Initial states. Function. And F is just the accepting state, so the ones that we give more relevance, and just the nice ones. So we say that Q is countably infinite. If it is countably infinite, then we just call it the automaton, a distributed automaton. And now we say that the distributed automata accepts a node of a graph if at some point it accepts the state of the node during the run when you're running the algorithm. So you have a vertex, and then this is just going to be the labeling of those elements. So I'm not mistaken, we continue. Okay. So yeah, so okay, let me just go back a bit. Now here, the idea that we will is to modify this delta, like how can we make this more general? So we have the power set of Q, but you could have neighbors that have the same state, and that is quite important. So we will change that, the power set for the multisets. So now, yes. So finally, distributed automaton, we start with the same, but just we change the delta, in which we have this MKQ and MKQ instead of the power set, and those are just the multisets. So multisets of bound at most K multisets, so taking at most K. And again, it's only work depends on the current state. But now the multiset is K by kappa, K. This is finite here. So you take K element, the first K elements in the of the multiset on the neighbors. That's why you care, and you can take copies. And so the first one is just for the Here. Oh yeah. So this one, the first one, is just the multiset of the neighbors, and the second one is the multiset of all the node states. Oh yeah. Okay.
Sorry for this silly question. What is a multiset? That's like a
Multiset. The thing is, a multiset when you have many times the same element.
Okay.
So you can have one.
It's a set with an allowed addition.
Yes. So a bit of intuition here is that, okay, you need to have a lot of information when talking about or why we want this. Is you want to have a lot of information because you may have, we will work with words and tokens, so some words may repeat, some tokens. Tokens are just parts of words. And why we care about the name? We care about the neighbors because we know that when you have a sentence, the neighbors are important. Yeah, like neighbors of a word is important. What is here? What is here? Yeah, like I have a dog. Oh, this part is important. But this part is important because this, if you only have this part, you could have something like I have eaten a pizza. So this is not a verb, this is a verb. So it's quite different. So you cannot say much without this, but with this one, if either is a verb or not, it immediately tells you if have here is an auxiliary verb or is just the verb to have.
This exemplifies what?
Oh, why we care about the neighbors.
Oh.
About why we don't only care about this, but also the neighbors.
Sure.
Yeah.
But another question, the graph itself is not part of the definition of automata?
No.
So you can apply it to different graphs?
Yes. So yeah, because the graph is going to be like the string, the input. The query that you send to GPT is
That's the graph.
That's the graph, yes.
It's a graph?
Yeah.
It's a very simple graph.
It's a very simple graph. A very linear, simple graph. I hear you see. Okay. So that explains this one. And now the question is, well, we care about all the nodes because it sounds like we are cheating. Yeah. We're getting all the information of the sentence. Why do we want all the information of the sentence? And the thing is, you don't see it in English, but you see it in, let's say, German. So in German, you have something like ich habe. You could have here ein or whatever, something that is not a verb, because in German, when you are in perfect, the verb goes here. So say gegessen. So I have eaten. So it's go at the end. I'm pizza.
This explains what?
Why we care about the global, all the nodes, the multiset of all the nodes. Not only the neighbors, but we also will need to see. Because the grammar could be a bit tricky putting something at the end.
K cap means you just take K?
K of them, yes.
So there's a linear ordering of which token, which.
The K thing is because a computer works with these float numbers, and these float numbers have a particular thing. And I will go there. Is it possible to see here? Or is it too dark?
I'd probably use another marker.
Right, this one. I will put it. So, okay, yes. So computers have a finite number of numbers. So when you start with adding a number, you have n. Then the thing with the numbers in a computer is that they are in the float, that we're going to work with floats. They are very dense around 0. But the farther you go, they become more spread. So for every element here, or whatever, n, you can start adding some n plus n, and you may find it. And so 3 times n, and so on. But there will be a point in which, let's say, this is kn, but n here is so small then when you add that here, this would be, let's say, k plus 1n is closer to kn to the next float number. So when the computer computes this, it says that kn is equals to k plus 1n. So it is enough for us to calculate k many. And obviously it's a finite number, but we have a finite set. Each number has some k, so there is a maximum k for the whole set. And that's the k that we have. You see, it's more a trick for computing but it's a trick for computing that makes the system work. Otherwise, we will have to work with reals, meaning you have to approximate all the reals, and then you will need, for example, infinite sequence for pi to do calculations, and that's not possible for a computer. But this makes everything, let's say, to converge the use of k. That's why we use k. Okay. Now that explains why we're going to use that modification of distributed automata counting. Of distributed automata, this is a distributed automata counting. And now, well, we have again the initialization function for the label that from node labels to initial state and the acceptance state. So we only change the power set. So, and again, if it's countably infinite, then we call it just a distributed automata. And we accept the graph, we accept the node if the graph at some iteration hits an element, a state, an acceptance state during the run. So if you see here, for example, we didn't say anything about for how long it's going to run. So in principle, it could run for an infinite, like we keep running until times ends. So the thing is when we put, okay, that's later. Okay. This was the example. So let's go for an example. Okay, go back. So we could say that the automaton runs for n iterations or just continue running. Well, there is an issue with that. It's like maybe you have an infinite graph, like you have infinite iterations, and you're trying to find the reachability problem. And even the only way to solve it is to run it infinitely many times, and then after infinitely many times, check the answer. You don't know if at 100 is going to find it, 1,000, or so on, or maybe never. The only way to say never is to run it infinitely. So we sometimes have to put a bound for the running. Now let's go for an example. Right. So here we have our graph. We have the node labels pi. So this is the initial state. So we have our vertices v, u, w. We have the nodes label, the pi of the powers of pi. So the v has p1, p2, w p1, u has p2, and that's the initial state. Okay, that's the initial state, but it's calculated by the function pi. So S0v, the initial state of v, is pi of pi p1 and p2, because that's what is there by the gradient function. And then, so in the round t plus 1, we have the graph, and then we have this vertex asks for information here, and then they send the state, because we're in the round, we're going to calculate the round t plus 1. So in the round t, the state here is SWT, and the one here is SUT. They send it to V. So now the updated state in V is SVT plus 1, that is calculated by delta, giving that the state of V is SDT, and the multiset of the neighbors is STU and STW. So this is a simple, in the case of where we were using the power set, just an example, no without the counting. Okay. So, formally. So in the round T, we have the global configuration, given in this sense, that goes from the vertices into the states. The initial state, each vertices has an initial state by the function pi. So we have Q prime. So the state that the subset of Q in the class when we're talking about just the power sets of the neighbors. So we calculate ST plus 1V based on STV and Q prime, that is the state of the neighbors at the T, at the time T. Okay, so when we talk about neighbors of V, we mean the out neighbors, and that's what I was saying, that the arrow that means the out neighbors. We are asking for information, just a convention. And a node is accepted, is entered to accepting state during a run. Just formal way of explaining the example. And here it comes the first result. And this is from Hela, Busisto, and some others from 2012. And they show that when you put a limit of iterations to the distributed automata, then that is the class of modal logic. So for every modal logic, there is a constant iteration distributed automata that characterizes. A constant iteration of distributed automata is constant iteration distributed automata are characterized by modal logics. So we can see that there is some connection with logic at this point. So let's go to the logic. So let's start with some other examples. So we have the idea of modal logic and temporal logics. So let's talk about modal substitution calculus. So let's call it a program. In modal substitution calculus is just two lists of rules. So a base rules that are going to be like the starting position, the beginning of the beginning, and the induction rule. There is just some rules to create more formulas. Okay. So the blue one, the base rule, is the ordinary modal logic. This is given by just the usual logic with diamond. I will explain what is a diamond. Just stay with me for how this works. Diamond is just asking if a neighbor has something, if it's true on a neighbor. Okay. And the red one, the way to produce the formulas is same as in the original modal logic here, but we add X, that is these rules. So you work in an inductive way to create more formulas. Let's go for an example. So here we have our two rules. We have C1, C2 until Cn, and then we have phi1, phi2 until phi n. Those are our rules. So x0i is Ci, as we feel from here. This is the starting point, the first formulas that we take into our program, create into our program. And then we iterate based on the red rules. So xt plus 1j, that's an I, yeah. So you obtain the xt plus 1i by, we go into the formula is phi I, and in that formula we substitute every occurrence of xj by xjt, because we have calculated xjt at the point. It's an inductive way to create with new rules. Okay, now we have to talk about the truth in the program. So we said that the program is true in NV, in M, a model M and a vertex V. So basically, M is going to be a graph. It's going to be one of these particular distributive systems. And it is true if x1t is true for some t. So the x1t T, this first part, this first, the ones generated by the first rule of inductor, is going to be kind of our accepting formulas. Those are the flags to say accept, don't accept. That's how we're going to create these iterations. Okay. So a program accepts a node V of a graph. So that's it. M is a graph and V is just a node. If there is some T, such that the formula XTI is true at V. That's how it is. So as you say, we are kind of in logic doing iterations to create some formulas, which kind of mimics what is going on in the automatons, like trying to change the states, which are kind of the truth values. Okay. And here, as I mentioned, like M is one of our distributed systems for a vertex. Sorry, a set of vertices in a graph. Okay, and finally, as I promised, so diamond. So diamond phi is true in NV, if and only if phi is true in NV. There's a typo there. Is phi is true in MU for some U such that U is a neighbor of V. So here is U. So just checking the neighbors. Okay. Now, Kujisto showed that this MSC and the finite distributed automaton have the same expressive power. So recall that the distributed automata, it could run infinitely. There was no limitation for how long it's going to run. So that have the same expressive power as the modal substitution calculus. Okay. Now let's see what's the connection with neural networks. Let's talk about graph neural networks. How much time? Okay. So a graph neural network. Let's define the graph neural network. It's a counting distributed automaton delta phi f that obtains that you obtain after a learning process. So you obtain this delta phi and accepting states after a learning process. So we're not talking about how to train the neural network, we're talking about the outcome of the training. That's after. You have the initialization function. So it gives you a vector for every node. You have some feature vector. There's the initial one, and then we have the transition function delta. So you have a combination function, and then you have an aggregation function. So typically this is a sum, but what you're doing is that this one codes all the neighbors. It is a all the neighbors of a vertex, send them into a vector, and then this one take the neighbors, the one that is obtained from the aggregation, and calculate based on the state of the vertex to give a new state. It's just code. So, for example, if you're in a node V, you compute the new state as t plus 1 at V as the combination of the state of V at T, so SVT, and the aggregation function of the multiset of the neighbors. So it's just coding. This is just a transition function. So it's a very particular transition function. And similarly, we can talk about that the GNN accepts nodes in the graph. It's at some point V gets an accepting feature vector. Same notion of acceptance and so on. So why I'm talking about graph neural network? Because what I mentioned, this system, the floating point numbers that are the ones that we use for calculation. When you use the GNN with these floating numbers, you get similar calculations to the real numbers we mentioned, and we can also add to the MSC the new diamond, like this this one, saying that they are at least k neighbors. This means there exists a neighbor, so it's blah. This is that there are at least k neighbors, such that a formula happens. And it turned out that these two are true. Have the same expressive power. So when you add the at least k neighbors to the MSC, you have the same expressive power. And when you apply So we're talking about after the training.
Okay.
But in the training, I do not know, but it might be true that maybe training the formulas is easier. It might be. I wouldn't
see. But the specificity is in the term, in the sense that we're getting here like universal approximations, like neural networks. With universal approximations, I mean like you can somehow approximate like any certain type of functions via graph neural networks, right? So is it like we're restricting to some kind of functions using any of these two architectures, or?
As far as I remember, we are not restricting. We're restricting.
Or like changing, or how does? So what is expressivity? Probably that's
expressivity. Okay.
What is expressivity?
Expressivity means that So this is also so in the GMSC, it gives like you have you get out some formulas. So the output in MV is 0, 1 is that in GMSC, and in GNN both you have some graphs MV, but the output here we know that is a vector that is, let's call it F1, F1, 2. These are floats, right? So expressivity here, and this is very important, from here to here, from GMSC is that for every of these ones, there is a neural network so that the graph here will have the same output here. So this will be 0, 1, in that direction. It will calculate the actual value, the actual truth value. In the upwards, this one you have to take bit by bit. So you have that F1 is called D1, 1, D2, 1, and then this is 1, 2. So you get a bigger, So from here is again, for every graph neural network, you can construct a sequence of formulas so that they will have the same. Arithmetic calculation, that's the part that's at the end, arithmetic calculation, because I don't want to just go through formulas and this matrix and this matrix. So go with start with the more intuitive part. Okay, so now let's take the counting fast global distributed automaton. This is basically, as we talked, the previous case. When we were talking about to modify delta to have multi-sets. So as the name says, we're counting the past. So we're counting like the context from the past, and then we're also counting the global context. That's what we already discussed when we add this the k multi-set. Okay, here you have that. Now we're going from tokens to, so the initialization function is from tokens to Q. Let me explain what's a token. It's basically a word or a sub part of a word. So you can think about it as what sometimes is called like as a Greek root or Latin root. So for example, in Finnish you have huominen, that means tomorrow. Huominen means tomorrow in Finnish, but huomisen means see you tomorrow. So it's clear that you have to make to cut here, because this is just talking about tomorrow, and this part is talking about some either the normal part or some prepositions about what's happening with the tomorrow. So the token will be this and this. So we have two tokens there. So we cannot talk about words or what we're going to play tomorrow. So that's the idea behind token. Okay. So we're just using tokens now. And finally, we saw we need to put some bound for the calculations. So n is going to be the output round when we stop the calculation of this automaton, and b is just going to be in the output. We care about the first b bits of the output, because after that could be just something that the automaton is using for do some calculations of changing states. So the b is just the part that we care about. So the b is that the automaton gives something like a very big string, but we care about only this part, and then we assume this is irrelevant. I wouldn't say it's trash, but it's irrelevant for what we want the automaton to do. Okay, so it's just a variation from what we discussed, just that before we were talking about accepting states, and now we're just checking about the state at that point. Okay. Any questions about this one? Good. Now let's talk about the logic that we're going to use. This logic is very simple. So we have the usual part of a logic, the propositions, the negation, the conjunction. This G, pre, if you remember, we used some diamond that was at most case, but this is just talking about global. So we say G for global. So globally, at least K vertices satisfies P. Yeah. So this is the part that checks the whole context, for example. And this is P, that is the suffix that checks the past. So in the past, there is a vertex that satisfies P. And that is the logic. It just is checking the past and the global. And it's just that the vertices. Okay, so this kind of makes sense to go we have this. Because now, so this talks about the input of our systems. So, as I said, we have sigma, that is just tokens. And let's define a label graph. Label sigma label word shape graph. So the set of vertices is n, meaning is n vertices. Just first one, second, third, fourth, fifth. Then we say that the edges are the successors. So this one goes here, it's here, 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 right? Yeah, that way. Okay. Okay. And the labeling function, there is some lambda, so here is some lambda 1, that maybe this is some token 1. Yeah. And so on. So here is just, you see, we're putting tokens in each vertex, so this is just when we ask, give me a recipe for a good pizza, or something like that. It's the sentence. It's a very simple graph. Now, the thing is, we have to get two sorted word shape graph. We add a new token that is the boss, beginning of string. So when you make a query, when you ask something, for example, you have here the boss, and is that yeah, here is the beginning of the string. Like here, the transformer will start adding tokens. Will start generating the answer. So if you see, this has to be unique, which is that only one vertex has the boss assigned. And now the prefix means that it's everything before the boss. So in this case, all this is the prefix at the beginning, but at some iteration of the transformer, maybe you have already a big string here, and then you're iterating. So from here, the boss is still the prefix, but this is the string. So boss is not always at the end. And the suffix is just the rest from the boss after. So in this case, for example, that we are here, so this will be the suffix. So it's going to tell you what it has been already produced or generated. Okay. So now is the arithmetics that I said is a bit tedious, but it's still a bit so. A strict future mask is that you take so you code the whole thing into a matrix. I mean, the matrix is just you here have here all the tokens, and here are all the vertices. The tokens there are not. So what you're doing in the mask is you're taking this part only without diagonal. So all this is 0, 0, and here you have some information. The idea is that when you're training the transformer, you don't see what you're training, because this is equivalent to what is up to here. So you're not seeing what the transformer is training. You see up to 2, otherwise you will be cheating and then you're not training something, you're not guessing. So that's the idea behind the masking. Sometimes you use it, sometimes you don't, and some iterations you do, some iterations you don't. The softmax is because you get at the end of the calculations, you get some vector x, and those are big numbers, whatever. So you want probabilities, you turn the vector into a probability distribution. That's what the softmax is doing. Just taking the output of the and turning it into a probability distribution. Okay. The attention head. This is the important part. So the attention head now here's with mask. So let's say like this. Attention head is this formula. With mask and without mask would be without here. But so the thing is, these three matrices, WQ, WK, and WV, is the important part. So this is the query. So it's what the vertex wants. This is the key. How important is what the vertex has for the query? Like one is saying, I need this. The other one is saying what the other vertex is saying, what you have is important or not for me. And this one is just calculating the value for the outcome. That's the idea behind. You have three things: the query, the important, and the calculation. That's it. So that's the formula that make all the revolution of AI. Yeah. Maybe I don't know if you can see there the neural network, but it's quite because that's the transformer. The rest is just the attention head, and the rest is just a couple formulas. But we multiply matrices because it works like this. V, CD, this is equal to A, this is U, AU plus B, C, U plus BV. This is equivalent to when you have here two vertices. Let's put here, let's put here V, let's put here U. And then we just put the usual weights that we talk about. So V here, we put V. This is AU. Ah, yeah, okay. Right, going the other way. So A, sorry, this is not A, okay, this is V, so is V, A goes here, V is D, yes. In this one, and C in this one. So this one will have the label, remember that it's going backwards information, so it's BV plus AU, this one's here, and here is going to be the other one, that is CU plus EV. So you can see that this kind of weight things of neural networks is just some matrix multiplication. So that's why we only talk about this formula. Okay, so let's continue a bit more with some formulas and things over there. So sometimes you just have way too many, or you need a lot of layers of attention. So you just concatenate them, you put mask, and you put like this kind of like the beginning of string, so it's the encoding. X. Yes. No minutos. Nice. And then multi-head cross attention layers when you have it's defined similarly, just that instead of having XX, you have X and Y. So you have X and Y, and X and Y, you have different layers, and it's have cross attention not coming just from one part, it's coming from also the other part. One was already guessed something. Again, this is just some multi-layer perceptron, and it's just this function. And again, this new W1 and W2 are some parameters of the bias. This is just some way to calculate and to make it do like to work the arithmetics. This is just the arithmetics behind the transformer. So here you have like what's encoding layer. There's just the multi-layer, and then you have the MSHS of X, and then you concatenate the layers, encode the layers, and then you have also the decoding that is just more of the same, because that is the Y, the part of the Y. So in the decoder you do need X and Y, and the other one you only need X, and then here you update it with Y prime. This is just some arithmetics. Well, not so many things, but describing how the architecture goes, how many layers and so on you're putting of attention, how goes back and forth. So this is the decoder length, putting many decoders together, and just the output is just again some multiply Y by some W that will just give you the. I mean, this Y is just what you get after all the previous multi-layers and so on. That gives you some matrix Y. You multiply by W, so you get the right length, and you add the bias. So that this is basically a transformer. You divide into prefix, suffix. You go put it as tokens. And then you apply the encoder, the decoder, depending how many layers you have, and then you plug the output, so it looks nice. And that's what it's giving you. So it gives you a matrix. And it's a matrix in the sense that in each vertex you have like something like this. So it gives you a matrix that in one is what corresponds. This is the output for one. This is the output for two, for three, two, for three. And it gives you this as you apply this of mine, you make it probability, and then it gives you like a probability of the tokens here, and then you check the last one, you choose. any person from the group, from the logic group in Tampere, me or Anticusisto, if someone has an idea for something, that collaboration, feel free to reach this. This is a very, very new field or research area. I think it has something like.
Can you go back for a second?
Sorry?
Can you go back for a second?
Yeah.
When you put the article, so I can download.
Ah. Okay, so this is the main result, like saying that those three things that we just defined, the logic, the automata, and the transformer are the same, but the transformer without the softmax because of the approximation of the flow. Thank you. Yeah.
For the talk, sorry for all the interruptions during the talk. I don't know if we can room maybe for one or two questions, since there are no talks after that, so.
No, but just very quickly, what do you expect later? Now we have a logic for transformers, which I mean, the last slide before this tells you that this is good. And now, you know, what is the power you expect to get from that logic? This is a very vague question.
Yeah, but let's say one is, as Daniel mentioned, probably this opens some like this is faster to train one of these others or not, maybe. Another is to finally understand that why, for example, when you ask to ChatGPT something, it comes up with something that was not written there, that it was taken from the context. So it gives some idea like that the transformer, what the transformer was calculating was the truth value of some sentences. And some sentences that we didn't see when we put the string, but the transformer kind of sees, you know, not it doesn't see it, but it is there by this theorem. So sometimes something appears and you're like, how ChatGPT knew that was happening.
So to summarize, logic may have descriptive power, but it might also have predictive power, which I mean depends on the logic. Not all logics have predictive power, but if they do, that'd be an explanation, perhaps. I don't know.
Yeah, I mean, another explanation or another thing is, for example, in your previous question, yeah, Daniel, if you train or if you find if you train a transformer and you find the formulas of the logic, then you know precisely what the transformer is doing. What are the sentences that it's checking?
Oh,
is this person tall? Is this person small? Has blue eyes? Has not?
that's very nice because the big problem that we have with neural networks is that we lose explainability.
Yeah.
You're giving exactly what's the formula that reaches some explicit output. Now people can say, oh, this output is because this was the reasoning behind it.
Yes, it's give a lot of explainability.
I would say that was the biggest thing.
Yeah.
That's very good.
You had another question?
No, this was something meaningful with respect to explainability that you mentioned that before I asked. Thank you.
That's one.
The concept of reachability. So when you started the whole, not through the logic, through the automata,
Yeah.
the whole concept of reachability, why didn't that, I guess, explain a lot of what was going on within the transformer architecture? Because I feel like there's a lot of examples and counterexamples over there with, like, what was the, oh, okay, we need to match this with logic because it doesn't explain it.
Yeah. So reachability was just some precise example of an automaton. just that for these are the tokens. But it could be a different side of things. So,
Yeah.
I don't know, maybe if you work with images, it's a color or a bit. I don't know. The logic is more global than that.
Can you help maybe comment that, please? I wonder if you can maybe encourage us to assist to your mini course.
Oh yeah, so tomorrow, like Wednesday, Thursday, and Friday, there will be a mini course in which I will just show the proof of this theorem. Okay, yeah, basically the proof is giving a transformer, just how to construct the formulas, giving a set of formulas, how to construct the automata, and how the CPG automata, and giving the automata how to construct the transformer. So you get a better view of what's going on, what's happening, how is the translation between these objects. I think it was the other way around, from here to here, and from here to here, and from here to here. The other direction was.
Okay, Miguel, thank you so much. I think we have a space outside.
Yeah, to just drink a cup of wine and eat something.
There is some networking space, so you can share with Daniel, with Miguel, and also with the professors of Oxford.